Hello viewers, today I have a video on a pretty interesting topic, and this is about a very well-known linear model, and this is generally seen for exponential growth and decay, and today I want to discuss exactly why the exponential growth and decay um, equation is the way it is, what are the principles behind it, and what are some other applications for it. And so we'll use our differential techniques to solve them, and we'll move on from there. So, throughout your schooling, you probably have, one way or the other, stumbled upon an equation that looks like this. You have some function that is equivalent to some initial condition, or more often than not, some initial population, multiplied by e raised to some constant k, and multiplied by t, which is time. This is a time-dependent function. And so, oftentimes you would find this earlier on in your math study. This would be used generally. Your initial population, for example, of bacteria, is generally already given. Your constant may already be given. And the questions you would encounter would be, for example, what is the population of bacteria after 5 years? Or something of this nature. Considering, like, for example, t equals 0 corresponding to the year 2000. What would be the population of whatever biological species it is after 13 years, right? So this would be some of the earlier examples that you might encounter. And then when you move on, you get more detail. The problems ask you to use tables and charts to discover what exactly the initial population might have been, or to discover what exactly the constant is. And moving forward, even after that, you'll start to get into discussing how exactly this formula comes about. And so that's what I want to discuss today. This formula can be used for all sorts of applications, from half-life in physics and chemistry, to carbon dating, to bacterial growth. So there are quite a few applications that are used, and it's really interesting to see what the concepts are behind it. So we'll start off with one idea, and that idea is that the the rate at which a given population grows is proportional to that population at a particular time. And so, speaking differentially, this is what this means. We can say, let's assume that our our population is represented by P, for example. So I would say that the the rate of the population with respect to time is proportional, and K being our proportionality constant, is proportional to uh, our given population at that current time. And so, a lot of times, this is the way I see it. Uh, to be more specific and even more accurate, uh, what I said previously would be translated directly to this, meaning that the rate of change of that population is directly proportional to the population at that given time. And so what we can do is we can take this first order linear differential equation, and we can solve it, and we can use those principles to derive this equation here. And so that's what I want to do today. And in future videos, I want to do some problems, and we can discuss some applications and some of the things that some of the assumptions that the equation makes, and how accurate they are overall. So now and we'll begin with our derivation. So starting off with the first order differential, it's equal to our proportionality constant and the population at a given time. And so what I want to do here is I want to solve this using an integrating factor. And so what we can do is we can write it in the pure definition form. And what we want to do is we want to isolate everything to one side, and we want to make sure that your differential aspect has no constant or coefficient there. So I'm just going to move the Kp over to the left hand side of the equation and then set that equal to 0. So I'll go ahead and do that now. So dp dt minus Kp is equal to 0. And so our integrating factor is dependent on the coefficient of our dependent variable. And so in the case of this differential, where we have a function that's dependent upon t, it's a function that's dependent upon t, and that function is p, which is the population, and that's what we'll be solving for when we get this. So p, the coefficient of p here is minus k. Be very careful there. If you use k as your integrating factor, you can end up off, and you might actually get the entire thing wrong. But there are some safe ways to check and make sure that you're on the right track. So I'll just go ahead and start off with our integrating factor, abbreviated int factor or int fact. Okay, and so the way this works is we take our function e and we raise it to this coefficient right here, minus k, and then we integrate that. So e raised to the integral of minus k dt. And so now what we can do is we can take the negative sign outside of the integral, and then we can integrate k dt, and that would be kt. So if we say that's equal to e to the negative kt. And some of you may be wondering, well, this is an indefinite integral. Why don't we have our constant c? Well, our constant c actually adds unnecessary complication in this derivation, and you'll actually find that quite often in a lot of differential problems that you'll encounter. You find out that a lot of constants are absorbed and some aren't considered because they add unnecessary complication. And I think this is one of those cases. I'll certainly look to find a better explanation if you're wondering. And if you do know a better explanation, certainly post that in the comments, and we can all learn from that. So once we find our integrating factor, which we've discovered here, it's e to the negative kt, what we do is we multiply the entire equation by e to the negative kt. And so what that will look like is, let's see if I can get a new page. We had dp dt t minus kp is equal to 0, what we want to do is we want to multiply this entire thing by e to the negative kt. That's our integrating factor. See if I can get this a little bit better. Negative kt. Okay. And so when we do this, I'll just multiply this out so we can see what exactly that looks like. E to the negative kt minus kp e to the negative kt, and e to the negative kt multiplied by 0 is still 0. And so now we can create our integrating factor. And so what we ask ourselves is, well, not our integrating factor, but our product derivative. And so we want to figure out what two components of this entire equation, when multiplied together and we take the derivative of that, we would find this this equation here. And so when you look at it very closely, you notice you've got kp, and the derivative of kp with respect to time, considering k as a constant, you find that that would be dp dt. And when you look at e to the negative kt, if you take the derivative of that, you find out that that is e to the negative kt multiplied by negative k, and that happens to be exactly what we have here. And so our product derivative would be p multiplied by e to the negative kt. And that's our product derivative. And if you want to check, you certainly can, and you will discover very much the same thing. So if we wanted to check really quickly, we could say, okay, well, we've got these two multiplied by each other, so we say, well, what's the derivative of p? The derivative of p is dp dt, right? And then we multiply that by e to the negative kt. Then we say plus, and then we derivate e to the negative kt. That happens to be negative, so the plus is essentially ignored, and that becomes e to the negative kt multiplied by negative k, which is part of this, and then multiplied by p. And so you get exactly what's up here. So we know for a fact that we're on the right track. And we set that equal to 0. That was untouched. And so in order to fully solve this, we have to integrate both sides, because right now we have a derivative, and that's not exactly what we want. We want a function of our population, and so that's where we want to get. We want to isolate p, and so we're just going to integrate on both sides. That looks more like an S, but there's good reason. And the reason for that is, if you can remember back when you were first learning about integrals, it was all based upon a sum, and it was based upon, more specifically, the Riemann sum, which is essentially the sum of a series of rectangles of various widths to estimate the area beneath a curve. And so the notation actually is reminiscent of that, by having something sort of like an S as simply a reminder, hey, guess what? This is yet still a sum. And so, you know, if you make an S, or it looks more typical, either way, it serves good purpose. So that's a little short sidebar conversation. But anyway, so you want to integrate both sides, and you want to make sure that you're integrating with respect to t. Both sides, right there. Okay. And so if you integrate a derivative, what you get is the function, right? So this is the function, and so that will, these two processes of integration and derivation, they cancel each other out, and then there you just simply get your function. On the other side, we have a constant 0, and that will become 0t plus c. And the reason why I say 0t is if we were to consider it any other constant, it would have been that constant multiplied by t, and plus c because this is an indefinite integral. And so we can go ahead and do that now. And we say that p multiplied by e to the negative kt is equal to 0t, which is 0, plus c. And for the purposes of this, I think I'll just keep it as c, and then we'll move on to the next page. Okay, so here we are, we've got a new fresh page, and what we had on the previous page is p, our population, multiplied by e, let's see if I can get an e raised to the negative kt, and that's equal to our constant c. And so because we want to isolate our population, because this is our function that we're looking for, we want to go ahead and write it divide by e to the negative kt. And so you'll have p is equal to c divided by e to the negative kt. And so we're almost there, but not quite. So we have e to the negative kt in the denominator, and if you just simplify this a bit more, noticing the negative exponent here, we can bring that to the numerator and get rid of that negative sign. So that will become c e to the kt. And so already it looks very much like what we started with. And no, I can't show you, but certainly earlier in the video you saw what we had, and you probably already see the similarity. And so right now you're probably wondering, well, what is c and why is it there, and what's going on with c? Well, c is our constant, and that constant in relation to the growth and decay linear model, that corresponds to your initial condition. And for the case of population, c would be your initial population. So instead of just replacing c with, for example, p naught, indicating that that's your initial population, I'll do a tiny short proof that you can do, and oftentimes I've done just for myself to make sure I'm just not heavily reliant on formulas. And so what you can do is you can say, first of all, notice that this function here is completely dependent upon t. And so if we say p of 0, what we're saying is that this is the population at time 0. And when we do that, based on what we have over here, we can say that that will equal c e to the k multiplied by 0. And we want to say that p of 0, being the population at time 0, is equal to the initial population. I think that's pretty intuitive. And so what we can say is that that will be equal to p naught. P naught, okay. It's more like a not p than a p naught. Okay. That looks a bit more like it. And so using our knowledge of exponents, we know for a fact that when 0 is in your exponent and this zeroes out, your function or your constant, in the case of this, becomes 1. And so what we will discover from this area right here is that reduces to c multiplied by 1, which is simply c. And that is equal, do a proper equal sign, that is equal to p naught. So that's our little simple proof of how that becomes our initial population. And so if we move on slightly further, we can see the full. We can say that the population, a time-dependent function, is equal to the initial population multiplied by e to the kt. And so this is very much what we had previously. So again, this is a really important equation or formula that you'll encounter in a variety of problems, from exponential growth and decay, half-life, bacterium growth, carbon dating, and there are just so many applications from something that seems like such a very short and sweet concept. And so this is what we've gotten here. And so in the future videos that I have planned, I plan to go through some problems, and we'll see what it's like to actually use it, and be very aware of the wording. That's very important of each and every single problem. Every single one is different, and once you get the gist of what's going on, you'll be able to solve each and every single one of them. So thank you for watching this video. I hope that it was helpful. I hope that it solidified some of your knowledge, and if you learned something new, or if there's something that I should add or remove, go ahead and post that in the comments below. And thanks for watching, and I hope to see you next time.